Module 13.3 and 13.4 are both going to take us back to optimization problems. However, in each of these modules, we're going to look at two different approaches for solving these optimization problems that now have multiple independent variables. So in this module, we're going to be drawing on some of the ideas that we already established in modules 7 and 9. Because again, essentially what we're covering with all these multivariable functions is the same general concepts as what we did with the simpler cases before. We're just now expanding this to have multiple independent variables. So for instance, our first step in finding any local extrema, which again is just that shorthand way of saying local maximums, local minimums, was to find some value for x such that the derivative of x was equal to 0, or the derivative of our function f of x was undefined. So we're going to make use of a similar idea when we have multiple independent variables. And this idea that we're going to make use of can be summarized by this theorem regarding local extrema and partial derivatives. So if we let f of ab be a local extremum for the function f, so this would be like our function f of xy, and then this specific ordered pair ab is our maximum, then for this function f, if both f differentiated with respect to x and f differentiated with respect to y exist at some point ab, then the derivative of our function with respect to x at the point ab should be equal to 0, and the derivative of our function with respect to y evaluated at a and b should also be equal to 0. So essentially what this theorem is saying is that if our function has a local extremum, then these two statements should be true. We should be able to take the first derivative with respect to x, the first derivative with respect to y, and if we evaluate it at this point ab, those results should both be 0. The problem is that the converse of that theorem is not true. So what we mean by that is that if we find the derivative with respect to x evaluated for two values for x and y, in this case a and b, and we can show that our derivative function is equal to 0, and we can do the same thing with our derivative with respect to y. We can find 2 points where that derivative with respect to y, or I'm sorry, find a value for x and y, where our derivative with respect to y is equal to 0, then the point AB may or may not be a local extremum. So if a local extremum exists, these two statements have to be true. If these two statements are true, it doesn't guarantee that a local extremum exists. So this process is only going to identify critical values. Once we've identified those critical values, then we need to run those through what we're going to call the second derivative test to determine if those are indeed absolute maximums, absolute minimums, or neither. So the second derivative test, if z is some function f of xy, and the point AB is a critical point, or critical value, and we know that capital A is equal to the second derivative of our function evaluated at x equals a, y equals b. So we'll find the second derivative of the function, evaluate it for those two specific values. We're also going to obtain a value capital B, which will be equal to the function differentiated with respect to x, then differentiated with respect to y, and evaluate that at that specific pair. And then we'll find another point capital C, which would be equal to our original function differentiated with respect to y, and then our second derivative with respect to y, evaluated those same two values for x and y. Then what we're saying is that if a times c minus b squared is something greater than 0, so strictly positive. And if our value for a is less than 0, then f of ab is a local maximum. So our process again is going to be to find these critical values or these critical points where our first derivative with respect to each variable is equal to 0. We generate these values for a, b, and c. We first evaluate this expression, ac minus b squared, check if that's greater than 0. Then we look at just a by itself. If that's less than 0, then this point that we found is a local maximum. So the other cases to consider is that if ac minus b squared is some value greater than 0, so the first part's staying the same, but in this case our value for a is greater than 0, then f of ab is a local minimum. So in each case here, case 1 and case 2, we need this expression to be strictly positive, and then the difference, whether it's a maximum or a minimum, comes down to whether a is strictly negative or a is strictly positive. Case 3 is that if ac minus b squared is less than 0, so in the case where this expression evaluated gives us some negative result, then f has no extremum at the point AB. This is also referred to as a saddle point, but it's enough for us to know that if we get this result evaluating this expression, we get something negative, that means that this point AB is not a local extremum. And our last case to consider for this test is if a times c minus b squared is exactly equal to 0, then this test fails. So in a case where this test would fail, we'd have to consider some other approach to finding whether we have maximum or minimum values. So in general, what we're looking for again is this expression ac minus b squared to be positive. When a is less than 0, we have a maximum. When a is greater than 0, we have a minimum. If that expression is negative, there's no extremum. If that expression equals 0, then our test fails.